In previous sections of our course, we have given a physical interpretation of the curl of a vector field. And in this section, I would like to take a moment to use Stokes Theorem to justify the conclusions that we came to in our previous discussions. So for the sake of this current discussion, let's suppose that V is a vector field in R3. So I'll write it like this. V is in V3. V is a vector field in R3 for which all of the component functions are continuous and have continuous first partial derivatives. So the usual assumptions under Stokes Theorem. So let's just write it this way. So let's say that this satisfies the hypotheses of Stokes Theorem. And furthermore, let's suppose that this vector field V represents the velocity field of a fluid flow. All right, so a fluid flow. And let's also suppose now that we have some closed curve C. So let's say C is a closed curve and it's oriented. And let's think about what the path integral of V dot dr around C is telling us now. So if we take the path integral around C, this closed curve C, so let's draw a closed curve C here, of V dotted with dr. So V dotted with dr. This, remember, is equal to the path integral of C around C of V dotted with the tangent vector ds. And so this work integral can be thought of as a projection of the vector field onto the tangent direction, the unit tangent field of the curve, the simple closed path here. So let's think about what this means, right? So if we're interpreting our vector field as a velocity, then v dot t, this vector field right here, or this component, this scalar function right here, this represents the magnitude of the projection of the velocity onto the tangent direction, okay, around the curve. And so this is the tangent velocity in some sense, tangent velocity of this vector field V around this curve C. So what do I mean by that? Well, let's pick a point. So let's say we have this point. So stay away from this supposed corner here. Call this P. The tangent vector, if we have an orientation that's going this way, then our unit tangent vector looks like this. And if our velocity field is maybe like this, then the tangent component is just the shadow, right? It's just the shadow. We can draw this in red. The shadow is going to look like this, right? And so the magnitude of that projection vector is going to be this v dot t. The magnitude of that vector is going to be v dot t. Now, there's another situation that's possible here, right? It's possible that the velocity could be pointing opposite in some sense to the tangent vector field. And in that case, we probably can guess exactly what we want to do, which is extend out the tangent vector, the ray determined by the tangent vector, and then take the projection in that direction, right? So let's make this blue. And so this blue component here, if the velocity is pointing in the opposite direction, the blue component would be the v dot t. The length of that would be v dot t for that case. So anyway, the point here is that the path integral of a velocity dot dr around this closed path C is going to give us, in some sense, it's going to measure the circulation of the flow around this curve. And you can see how these tangent components are going to circulate around the flow. And so this right here, this is the circulation. So this is the circulation of the flow. We'll just call it circulation. Sometimes this is called gamma, by the way. So this is the circulation of the flow around this boundary curve C. All right, well, let's now try to apply Stokes Theorem, but to do this, let's make some assumptions here. So let's say that we have our flow field, we have our flow V at a point P naught in space. All right, and let's choose a small circle. So I'm going to draw our point P naught over here. Let's choose to enclose our point P with a small disk, okay, a small disk. So in other words, let's let C sub A be a small disk. So the idea here is that A is a small number of radius A, centered at P naught, all right, at P0. And so again, the idea here is that we have this small disk of radius A. You draw it big enough so you can see it, but in your mind, A is very small. Okay, and then C naught, so I said a small disk. I want C naught to be the circle, okay, the boundary circle of this thing. And I want it to be positively oriented. So I'm going to say there's our C, let's call this C sub A. I keep saying C naught. P naught is the center point. C sub A is the circle centered at P naught of radius A. And then we can say, all right, the interior disk region, this can be called S sub A. So that's the surface determined by the simple closed curve, which happens to be a circle here. All right, now what we want to do, so in Stokes Theorem converts our path integral, which we now know we can think of as a circulation. It converts this path integral into a surface integral, but the surface integral does not integrate up f, it integrates up the curl of f. All right, and in our assumptions for Stokes Theorem, so I just wrote here, it's our v. When I get back down there, we need to swap out our f for a v. Our vector field is v in this case. But the hypotheses of Stokes Theorem say that the first partial derivatives of v must be continuous. And so what that tells us then is, under the assumptions of Stokes Theorem, the curl of v is a continuous vector field. All right, it's a continuous vector field under our assumptions. Now, why is that important? Well, as we know from our studies of now 3 semesters of calculus, continuous means that the nearby points don't vary too much from the values of the vector field at nearby points can't vary too much, right, from the value of the curl of v at the point P naught. And so what we learn is, because of this, we can say, all right, the curl of v at nearby points P is about the same as the curl of v at P naught. And again, this about the same, this approximately equal, is only true because we are imagining A to be very small, and of course approximately can have different meanings as well, right? But this is going to be true for all P by continuity, right? For all P in our little disk S sub A. All right? So at this point, what we can do is we can apply Stokes Theorem, and we can keep in mind, so we're going to apply Stokes Theorem to this tiny, tiny disk that's centered at P naught, and we are going to see what happens, okay? But we're going to keep in mind that we can replace the values of the curl by a constant vector field, and that constant vector field is just going to be the value of the curl of V vector field at the center point, okay? So now we're ready to call in Stokes Theorem. Stokes tells us, ready? It says that the circulation, right? The circulation around C sub A, so the circulation around this tiny disk, is equal to the surface integral over the entire disk, S sub A, of the curl of V dotted with ds. But of course, how do you actually compute this? When we have a parameterized surface, we have one way of computing this, but in general, the definition of this is to compute over S sub A the curl of V dotted with the normal vector field, and then integrate up with respect to surface area. Okay, but what we're going to do is these two things are both functions of P on this disk, right? And so we can replace this, say this is about the double integral over S sub A of the curl of V at the center point P naught dotted with the normal vector at P naught ds. And at this point, this term is a constant, so I've replaced the integrand by a constant dot product, so this is a constant number at this point, and this can be factored out, right? And so this is then equal to the curl of V at P naught dotted with the normal vector at P naught times the surface area of S sub A. So this is just the area. This, remember, we chose S sub A to be a disk, right? The area of this disk S sub A. And of course, that was a disk with radius A, so the area is pi a squared. So this is now, this circulation is about equal to, it's approximately equal to, the curl of V at the center, dotted with the normal vector at the center, times pi a squared. Okay? So again, this is not exactly equal, but the idea is, you can probably guess at this point, what are we going to do? We are going to take a limit as the radius gets smaller and smaller and smaller. So take a limit as A approaches 0, and as A approaches 0, this approximation gets better and better and better, and in the limit, these are equal at the point, right? So the circulation is equal to this limit at the point. But the way we're going to approach this is the following. So instead, we are going to take this to be the following limit. So the curl of v at the center, p naught, dotted with the normal vector at p naught, this is going to be equal to the limit as a approaches 0 of 1 over pi a squared times the circulation. So the circulation c sub a v dotted with dr. And this is just the circulation around the tiny, tiny circles centered at p naught, right? And so as we take the limit here, this limit should exist, and we'll get a number here. And so what we end up with is a relationship between the curl and the circulation, right? They're not exactly equal, but they are closely related to each other. And so what we can conclude then, by this Stokes Theorem argument, right, that the curl of this velocity field at any point p naught, right, is closely related to, or in some sense it's related to the circulation of the flow. All right, it's related to the circulation of the flow in the plane that is perpendicular to the normal vector, right? So it measures the circulation of the flow about the normal vector n at p naught for each point p naught, right? And so this is the reason for considering the curl to measure rotations of the flow. In some sense, it's a circulation, right? So it measures the circulation of the flow at every point, or you can think of that as rotations of the fluid as the fluid flows.